So let's talk about section 4.3, one-to-one and inverse functions. So in this section, we're actually going to determine whether two functions can be inverses of each other. They're also going to determine whether the function is one-to-one. We're going to find inverses of functions. We're going to graph them, and we're going to talk about their limits on their domains. So let's start with what we mean by inverse functions. So functions itself, f and g, for which you might have f composed of g, when you plug in and make that composition of f composed of g, if when you simplify it all the way out, it equals x. And if you go the other direction with it, g composed of f, and you simplify it out and you get x, then technically these functions, f and g, are considered inverses of each other. So in this case here, we would denote one of them, we'll say g, and call it by f inverse. Now that little -1 part on the function that you see there is not an exponent. It's literally a notation to talk about it being an inverse, because f is not a variable. It is a name of a function. Okay, so let's kind of understand this, like how do we find them? So I'm going to give you two functions. So let's give you f of x equals 9/5 x plus 32, and we'll let g of x equal 5x minus 160 over 9. Now, these are actually the functions that can be used to convert a temperature from Celsius to Fahrenheit. And then the other version is basically the going from Fahrenheit to Celsius. So to see how these two conversion formulas for temperature are related, because we know that they have a relationship. We use Fahrenheit here in the US, but most places outside of the US use Celsius. So these functions should be related, since one is going from Celsius to Fahrenheit and the other one's going from Fahrenheit to Celsius. So let's see how they're related by using the composition to determine whether or not they actually are inverses of each other. So to start us off, I'm going to kind of just look at the functions itself, and let's compute f composed of g. So we'll start with this one first, okay? Now, again, remind yourself, for those of y'all that are my color people, for the visual learners, I'm going to make the f function red, and I am going to let the g function be green, okay? And that's just to kind of help me out with the color coding of it. So we're going to do the first one here. Okay, so we're going to take the f function and we're going to plug in the g function there. Okay, and again, remind yourself that g function, again, I'm using a separate color here. You can write it like this if it makes it a little bit easier to read. So it looks like basically the g function is inside the f function. I know that kind of makes it a little bit easier for some students to visually see it. Now remember, the f function itself is 9/5 x plus 32. Okay, and so from here, you'll notice instead of me writing x, I wrote a set of parentheses because that's where the g function is going to be plugged in. Now the g function itself is 5x minus 160 all over 9. And again, all I did was just plug it in everywhere I saw x in the original f function there, and then we're going to simplify. Okay, so in our case of simplification here, we are going to get 9 times this big fraction, which also has 9. So those are going to cancel out really nicely, leaving me with 5x minus 160 all over 5, and then this plus 32, because again, that 5 is only being multiplied to the parentheses. As I noticed there, if I divide everything by 5, I'm going to end up basically with, oops, hang on, let me erase that 5 there. I'm going to end up with, let's see, 5 divided by 5 is 1. So this is going to be x minus 32 plus 32, which simplifies all the way out to x. So this basically means that f composed of our g of x, when I plug in the g of x function, I get x. The whole thing simplifies to x. Let's go the other way. So let's go g composed of our f of x. Okay, and let's see, what does that equal? Now, again, remind yourself, I said the g function there is the one on the outside, and the f function this time is the one on the inside. So in our case here, we're plugging in the f function. Okay, so we're going to start by just writing the g function, which is 5x minus 160 all over 9. Okay, now in our sense here of what we've done, this one basically had a fraction, and in the fraction is where I'm putting in the 9/5 x plus 32. And when I start to do this kind of work and simplify it out a little bit here, I begin to notice I end up with basically 9x plus 160 minus 160 all over 9, which is going to give me 9x over 9, because again, those plus 160 and minus 160 add to be 0, which ends up equaling x. So the composition of these two, as I work my way through them, when I do f composed of g or g composed of f's, somehow cancels everything out until you're left with just a plain old x. Now, because I'm left with that beautiful plain old x, either way I went with it. What that means is the functions are basically inverses of each other. So we can say that basically f and g are inverses. Okay. Now, normally you would take one and name it as the inverse of the other. So I can say that basically f and g, let g equal f inverse, or I can say the g function and then let the f equal g inverse. It doesn't actually matter which one you start with, just make kind of note of which one is the inverse that you want to use. Now, since we're dealing with inverses, let's talk about one-to-one. Now, a function is considered one-to-one if for each output there's corresponds in the function with exactly, and that's the key word there that you want to pay attention to, is exactly one input. So each output goes to exactly one input. Okay, hence the name 1-to-1. Now, this basically means that for every element in that domain, there's really only going to be one element in the range. Now, we've seen this before, but we haven't really given it the name 1-to-1. And there's different types of functions out there, but this one is very important to know whether it's 1-to-1. Now, remind yourself that when we looked at functions back in early on, we talked about functions, and if I gave you a graph of, let's just say, we'll say x squared, and I graph it, remind yourself, in order to determine if something was a function, it had to pass what we call the vertical line test. So I would take a vertical line, and that would mean it was a function. Then now I'm talking about one-to-one functions. So it's something extra added on to being a function. So it already passes the vertical line test. Now we want to know if it's one-to-one. And to do that, we do the horizontal line test. So I'm going to take that graph, and instead of doing a vertical line now, because we already know it passes that one, it's a function. We do the horizontal line test now. So we draw the horizontal line through it to determine whether or not it is one-to-one. So all you have to do is literally put it in the calculator and take a look at it. So let's do that. So let's determine if each one of these functions is 1-to-1. And to do that, that means we need our calculator, okay? There is a way to do this by hand, but it does involve quite a bit of calculus and things like that, and we ain't going to pull the calculus out. Okay, this is math modeling. We're kind of like in the algebra realm here, so that means we're going to rely on our calculator to do a lot of work for us. So I'm going to put in y1, 5x to the 4th, and then I'm just going to hit graph. Now remind yourself, if your domain is if you've been playing with your graph a lot, you might want to hit zoom 6 just to make sure that it is straight and got the beautiful standard viewing window. Okay, so here is that beautiful graph there. Okay, go ahead and pause and take a second and see, is that one 1-to-1? Let's go ahead and with the second one. Okay, so I'm going to go ahead and put the second one in. Again, x to the 5th and then minus 2. Take a peek at that and give yourself a second and pause to think, is this 1-to-1? Okay, so let's, again, you've already graphed them. I've already shown you how to put them in the calculator. Let's look at that first one there. So that first one, remind yourself basically what we're doing in order to determine if it's 1-to-1. And this is where you want to pay attention to the keywords in the function. Determine if the function is 1-to-1. Now, they don't even have to continue on by saying using the horizontal line test. All they have to ask you is determine if it's 1-to-1. If you see this word determine 1-to-1, that automatically should tell you to use that horizontal line test. So I'm going to take a horizontal line. Now, I know in the calculator, when you took a peek at it here, and I'm going to pull my calculator back up. And just so you can see, when you look at the calculator, there is no horizontal line drawn, okay? So there's nothing there. So what that means is basically for us, we have to kind of imagine a horizontal line, just like we did with the vertical line test. And you're going to imagine that using multiple horizontal lines, so like just a ton of them, okay? If at least one horizontal line goes through and it hits more than one time, it automatically fails. So we can say that it is not one-to-one. Okay, now take a peek at the second graph that we did. And again, take any horizontal line and again, try yourself with multiple ones. Now, this is the only place that I'm kind of like, I don't know a little bit here. Now, remember, our graphing calculators are not the best. Okay, their screens are not these, you know, you got a better TV screen or probably even a better computer screen than your calculator does. Okay, so the calculator is, if you can see, this is kind of like a pixelated style drawing. So it is a little hard for the calculator to really get in there and draw a really pretty smooth line. If we were to go in and take a good look at that kind of area that I'm kind of curious about. So again, like I said, it's very, very pixelated. And let me go ahead and make that screen super large on the side here so you can really kind of get into it. So you can see it's very, very pixelated. And that's why I was like, just to kind of go with it for a second. If you want to zoom in, okay, around this area here where we're just really, really unsure, you can. And as you can see, like it looks like it's a straight line, but again, these are just the tiny, tiny, tiny point movement. And again, as I keep going closer, this little part right here gets smaller and smaller being straight. It's not that it's straight for a very long time, okay? So what it is just the calculator cannot show that very small, tiny movement very easily at all, okay? And if I were to adjust my window in any form or fashion here, and I mean, I can do this quite a bit with adjusting that window. Let me put this at like say -5, and we'll put this at like 1. We can see that this part right here gets smaller and smaller the closer in I get, and you can still see that same idea, okay? So with that being said, and like I said, I know I've just made that like really, really large over there for you guys, is what I want to take a peek at and really kind of look for is it's an obvious fail like this one is. Like when you go through, it's like bang, bang. Here, when you can kind of put that horizontal line, it only looks like, it looks like it's straight and flat, but it's really not. So they're really obvious when they fail. And so this one is actually one-to-one. Okay. So my B question there is one-to-one. Now, why do we go through this whole thing to determine if something is one-to-one? Well, that actually helps us determine inverse functions, okay? Now, remind yourself that basically what happens when we're doing inverse functions. An inverse function basically is a function that basically satisfies where A and B will basically be flipped in reverse and become B and A, okay? So when you take the really cool part of that and actually do the composition of the two, the composition actually ends up giving you a X only because pretty much X and Y switch places, and that's what should simplify all the way down to is the beautiful function of basically Y becomes X and X becomes. So that is actually what's happening with inverse functions. And we check to see if it's possible by checking to see if it's one-to-one. Because basically for every one X value, there should only be one Y value. So when we do the flip, the inverse will end up being a function as well. Now, this also leads into domain and range. So let's go ahead and bring back up domain. So the domain of our function, F, has now become the range of its inverse. Okay, and the domain of G has now become the range of the F function. So if you're dealing with those, so think of it this way, whatever you might actually have. So say I've got F and we're going to have our domain. That's an O, I promise. And then you've got your range, whatever it might be. Okay. and then your inverse here. And then you're going to have its domain and then its range, right? So say I'm going to give you an example of some random function. I'm not even going to like go super deep into it, okay? Oops. Let's just take a look at, say, we'll let the f function be, how about x squared, okay? So our domain automatically there is all real numbers. When I go to the inverse, no matter what the inverse looks like, the domain has now become the range of this inverse function, okay? And when I start looking for the range there, now the range of this function is going to be from 0, I need a bracket because it actually equals this, to a positive infinity. That will actually switch and become the domain of the inverse itself. Okay, so that's kind of what's happening, is that like switch between them, whatever they might be. So let's determine first if f of x being x to the 5th minus 1 has an inverse function. And then we're going to verify that it has an inverse function, and that function is actually x to the 5th minus 1. And then we're going to look at the domain and range of each one individually, okay, and how they relate to each other. So this is kind of an interesting wording, and I really want to point out that really kind of cool wording. It says determine if it has an inverse function, right? Now, this is a little bit differently than what we have looked at already. And basically, this is just a fancy way that says check if f is 1-to-1. Okay, that's literally all it's saying. Determine if it has an inverse function. Pretty much just check if it's 1-to-1. If it is 1-to-1, it has an inverse function. Okay, so that means we need to pull out our calculator. Okay, so I'm going to go into my calculator. Bang. Okay, so here's my calculator. Let me make that a little bit bigger there. And we're going to put in my x to the 5th minus 1. Okay, and I'm just going to hit zoom 6 because I was playing with the window a little bit there. And again, remember, I told you they're really, really obvious when they fail. So that looks like this is going to pass my beautiful horizontal line test. So I'm going to say, yes, this beautiful thing is 1-to-1. Okay, so we're nice and good there. So now let's determine whether or not it basically has the inverse of the 5th root of x plus 1. Now, in order to determine that, that basically means I need to determine f composed of g and g composed of f. Okay, so I'm going to literally plug the g function, which in our case here is basically what our inverse function is. And then we're going to basically plug in the other one. So like it's literally the same thing, but normally we would use f and g. In our case here, just kind of think of the fact that normally I would say verify that f inverse is that, or basically think of it as like this is g. Okay, however you want to name it. Okay, but it's always basically take the two functions and take the composition of the two. Now you want to go both directions just to verify. So if I take f and I plug in the 5th root one, that means I'm going to have the 5th root of x plus 1 to the 5th power minus 1, which again, the 5th root and the 5th power are going to cancel each other out, leaving me with x plus 1 minus 1, and the plus 1 and minus 1 are going to nicely cancel, leaving me with just an x. And then when I go the other direction, plugging in the x to the 5th minus 1 inside that 5th root, that means I'm going to literally have plus 1 and minus 1 are going to cancel out, leaving me with x to the 5th. And I'm taking the 5th root of it. So 5th root cancels out the power 5, which again leaves me with that beautiful power 1. So yeah, it does actually work out really, really nicely. Okay, so yeah, we basically verified that they are 1-to-1. So remind yourself again, kind of the key things here of what we're kind of doing. As if I just say determine if it has an inverse function, that basically means check to see if it's 1-to-1. Okay, so kind of a little extra part there. But when I say the word verify, okay, so when I talk about verifying something, so if I say verify, that these two functions are inverses, that basically means that you need to kind of do the composition of the two functions and verify that they come out both with x at the end. So now let's find the domain and range of each function. Okay, now again, if you are struggling a little bit with this, one of the best things I can tell you to do is start with the domain, and we should be able to do the domains without any issue with looking at the graph. But if you're not sure, maybe you should try and take a peek at your graphing calculator. So x to the 5th minus 1, I'm going to ask myself that series of questions. Is x in the bottom of the fraction? No. Is x underneath an even root radical? No. Is x in the piecewise function? Is it a word problem? No and no. So therefore, my domain here, okay, is going to be, and that D looks a little strange, so hang on. There we go. Okay. There, turn the pen back on. Is going to be a negative infinity to positive infinity. Now, those same questions also worked very well for this as well, which will also be negative infinity to positive infinity. Now, your range may be a little bit harder. So this is where definitely maybe pull that calculator out. So here is the graph of x to the 5th minus 1. We did it just a moment ago. So there it is in y equals. And we can we can verify and see that this graph does go left forever and it does go right forever, but it also goes down forever and up forever, which means my range on this one here is also still going to be all real numbers. Okay. Now, when I take back and put in the 5th root, so if you're not sure how to put a 5th root in, let's do the 5th root real quick. So we're going to start by hitting 5. And then I'm going to go to math, and I'm going to hit number 5 here where it says x root. And that's going to put in the 5th root there. And then I'm just going to type in my x plus 1. Now, I do want to be a little cautious because for those of y'all that have that TI 83, go ahead and hit that 5, and then you're going to hit math, and then again, number 5. This is going to be the same. But for you guys, strongly encourage some set of parentheses there. You're not going to see it where it has the line that goes over it. And so you are going to definitely need those set of parentheses to get this graph to show up this way. Okay, now notice again that this one does go left forever and right forever. It does actually go down and up forever. So again, it's slow movement there of going down and a slow movement of going up. So again, that is also still going to be all real numbers. But in this case here, I want you to kind of think of it in terms like as basically, and let me switch colors so you can kind of see this movement here, is that this domain has literally gone to this. Okay, because they are inverses of each other, and that this range has now gone here. Okay, so it's not necessarily as visible to see when you just see negative infinity to positive infinity, but what we can do is we can visually graph it, and it does help us out there. So basically the 5th of any real number is decreased by 1. So that is basically kind of the domain why it's all real numbers. And basically when you take the 5th root of anything plus 1 is still going to be a real number, which is again why it's all real numbers. But again, if you're having a hard time seeing that kind of switch up between the two, let me go ahead and put them both in here. So let me put in that x to the 5th minus 1. And pretty much you kind of see how like basically they kind of switch points. Okay, so if I were to look at the table here, if I look at 1, 0, you'll notice that 0, 1 is there. If I look at say 3 and then 242, I would need to look at 242 for the x value there. So let's do a quick look to that. 242. It should have a y value of 3 now. 242, y value of 3 on the red one. So they literally are switching places, okay? Now be aware that, okay, I did that in the table and it was really kind of hard to see because the table, these numbers get big so quick, okay? So as you can see in that table, like they got really big very quickly, okay? But you can kind of see it a little bit in these smaller numbers here in this area. So 1, 0 has now become 0, 1. If you look at, say, -1, -2, you see -2, -1 here. So again, they are kind of those beautiful inverses of each other. Now, we just determined whether something is an inverse of each other. Let's actually determine how to find it without being told what it is. So say you are given a function, but they don't tell you to verify it. They actually want you to actually find what is the formula that gives the inverse. These are basically the steps you want to use. So before you can even go about into this here is first things first, okay? Please understand that first, determine if the function is 1-to-1. Okay, if it is 1-to-1, then you can do all of these steps really nicely and easily. Okay. Okay, so step 1, and you can pause it here if you want to write these down. I'm going to kind of walk us through these steps really kind of with a problem. It's a little bit easier. So the first thing I'm going to do is I'm going to pull out my graphing calculator and I'm going to go to y equals, clear out all the stuff I got here. Ooh, I got tons of stuff in there now. And I'm going to plug in 2x plus 3. Okay. I'm going to graph this and I'm going to kind of do that for horizontal line test. Now it passes the vertical, so we know it's a function. They even gave us a way that it's function notation here. But I do my horizontal line test and it does pass that horizontal line test, so we're good there. Okay. So now basically step 1 of this process is we want to take this f of x and remind ourselves that it is y. Okay, step 2. Now I'm going to switch colors for step 2. Again, this is for my visual kids, but this also works for anybody else. But I find it really helpful to kind of switch up colors when we do these ones, just because it makes it a little bit more visual and you're kind of like, oh, right. So step 2, once you've changed f of x into actually what it is, it's a y. We basically, step 2, interchange x and y. So everywhere I see y, it's now going to become what we say x is. And everywhere I see x, it's going to become a y. Okay. Now, step 3 is you're going to take this process right here, and I'm going to change this and actually solve for y. So we are going to solve for this y that we have now put into place. It's kind of like the new y. So start by solving for y, and we've done this before. So we're going to subtract 3 from both sides. X and y, x and 3 are not the same thing. So this is going to become x minus 3 equals 2y. I need to get y by itself, so I'm going to divide both sides by 2. So we get x minus 3 all over 2 equals y. Okay. And last and final step. Okay. So we've just done all that. Final step is basically just switch it to f inverse. Okay. So the last thing you want to do is you want to take this that you solved all the way out for and now say f inverse, or whatever the name of the function is. Okay, so if we started up here with g, I would say g inverse. If this was h, I would say h inverse. And that's it. Okay, let's try this again. So the more practice we do, the better we'll be, right? So step 1, verify that this is 1-to-1. Okay, so go ahead and take your calculator out and verify it. So I'm going to start off by reminding myself that this is y. Now, I know some people, they write down the function like this and then they just cross it out with that. That works perfectly fine. Now, in the next step, as we work it, remind yourself that basically x becomes a y and y becomes an x. Again, I strongly encourage a change of color for my visual people. So this becomes x and this becomes y. And in the process here, what we're going to do is solve for the new y. Now, I am going to be a little cautious, and why I'm going to be a little cautious is notice where y is. Y is in the top of a fraction, as well as it's being multiplied and added by stuff. So what I'm going to do is I'm going to start by multiplying both sides by 5. Okay, that's going to leave me with a 5x equals. Now over here, the reason why I multiplied by 5 is because I can cross them out, leaving me with 4y minus 3. Then I can add 3 to both sides, And again, I realize 5x and 3 are not like terms, so they're just going to be those side by side. And last and final step will be to divide by 4. So we have y equals 5x plus 3 all over 4. And again, I'm just going to no longer make that y. I'm going to change it to the inverse of my function there. And again, you can leave it as this really pretty big fraction. That's perfectly fine. Okay. Now, let's take a peek at those graphs. So the graphs are really, really cool. And again, when you graph them on the same axis, that kind of allows us to visually see it. So I'm going to put in 4x minus 3 over 5 on one side. And then I'm going to put the 5x plus 3 over 4 in the other side. So I make one y1 and the other one y2. This will be really easy to see for those of y'all that have a graphing calculator. For those of y'all that have a black and white graphing calculator, it's a little bit more, a little harder to visually see this. So really pay attention when you hit the button for graph, watch which one graphs first. Now you should end up with a graph that looks something like this. And again, remind yourself that basically every point that is x and y literally switch places. So in my case here, I have x equals 3, my y is like 4.5, right? So if I go to 4.5, notice that my y value is 3 here. So again, every point is kind of just flipping about this line. And this line that it flips about is basically y equals x, because what exactly have we done? We literally interchange y equals x. Every x became a y and every y became an x. So the graph should be perfectly symmetric about that. Okay. And that's actually kind of where it leads into the next part of this, is that graphs that are functions that are inverses of each other will always be perfectly symmetrical. Okay, so even though they're perfectly symmetrical, let's talk about some of these functions. And again, still just practice on solving and getting those inverse functions there. So with my inverse functions, again, no matter what I name the function, so say if I name it g of x, the rules are still going to be the same. Basically, take that g of x and replace it with a y, okay? And then from there, you switch x and y, and then we go about our solving process. Now, I've already done this one here, and I've put in my beautiful solving. But what I wanted to bring to your attention, where a lot of people kind of forget a little bit here, is I had a power of 5, and that power of 5 stayed on the y value, right? So when I get to the point where I've solved out for y, y still has the 5th power on it. Well, the opposite of a 5th power is a 5th root. So kind of remind yourself that basically if I have a root, its opposite is its power, and the power is its opposite is its root. So they kind of undo each other, and that's why we end up with a 5th root here. But remember, when you take a 5th root, if it's a power of 5 here, it's the 5th root of the entire other side. Okay, so keep that in mind when we look at these. So let's try to find the inverse of a new function, but let's also state our domain and range. Okay, so that way, and this one's going to be a little bit more visually pleasing so we can really see that kind of uniqueness of how it looks. So again, I'm going to plug it into the calculator, verify that it's 1-to-1. I'm telling you it is, so it is 1-to-1. And so we're going to start by basically reminding ourselves that that beautiful thing is y. And then we're going to go, okay, well, x equals the square root of 3 minus y. So they switched places, right? Okay, so they've switched places. So now I got to solve for y. But in my process of solving for y here, y is stuck underneath the radical sign. So I have to kind of get rid of this radical first. So remind yourself, what was the opposite of a square root? Well, that would be a power of 2. Okay, and again, if you need to visually see it, I'm going to put it in a slightly different color there. Oh. And I don't know why I'm hitting it to where it says like this is that. Is basically what I'm doing is I'm taking the power of 2 of both sides here, And that's where this power of 2 kind of cancels out that square root, but it stays over here, okay? And that's why, like I said, it's a little unique in that sense. Now, in our case here, I am going to have to just basically subtract my 3 over. So I get x squared minus 3 equals a negative y. That negative is still in front of the y. Do not drop it. But at this point here, I do need to get rid of it by dividing out by -1. So that way we get y by itself and it's positive. And I end up with a negative x squared plus 3. Now, let's just look at this graph right here. Okay, so for the g function itself, the domain of g, this is where I have a small bit of an issue. X falls under an even root radical. So remind yourself that for your domain of your g, we had an issue with that. And that meant that basically 3 minus x has to be greater than or equal to 0. Now you want to solve all the way out for this. Now you can solve this a few different ways, but basically what I'm going to do is I'm going to subtract my 3. I'm going to get negative x is greater than or equal to -3. I'm going to divide by -1, and I have to remind myself anytime I have inequalities, that's that greater than or equal to symbol, and I divide by a negative or multiply, that inequality sign switch places, which means that my domain here is basically x is less than or equal to 3, meaning it should go from -infinity to 3. Now, guys, we've done this a little bit before. If you kind of think about it, this is basically transformations. That negative basically inside is a horizontal reflection, meaning that it reflects over the y-axis there. And then that 3 inside is that horizontal shift. Again, that horizontal shift is going to be, remind yourself, this is a positive 3. So we are shifting to the left 3 units. Okay. Okay, so that's my domain, and that domain has now become the range over here of the inverse. Okay, now let's see if we can find the actual range of this function. So again, if you're not familiar with this function, it does make it a little bit harder. And I strongly encourage you to use that calculator. Okay. Domains you should be able to kind of do by hand, but in case not, the calculator is there for you. But the range might be harder to do by hand. Now, if you know your basic graphs and you do the transformations on them, then you should actually know what your range is, just because of knowing the base functions. You should know their base domains and base ranges. And then when you do the transformations on them, you can use that whole, well, I shifted it up, down, left or right, stretched it or shrink it, and that how it affects the domain or range. Okay, so in our case here, we can see again, that's where it went from 3 all the way to -infinity on my axis. So we always say negative to the positive number. Okay, but I also noticed that I don't have any y values down here that are negative. So it kind of starts here at 3. So let me double check what that number is. So I'm going to go into my table, and I notice at 3, the y value is 0. And then it just kind of starts getting larger and larger. Again, it's growing. And again, I'm talking about the y value. So I don't care that it's going off to the left. I'm noticing that it is moving up and up and up and up, which means I'm going to have a positive infinity for that y value there. So my original function here, the range of our g function is actually going to be 0 to a positive infinity. Now, what that means is that when I take a peek at my domain of the inverse, the domain of the inverse will match the range of the original function. And this is where you can kind of see it a little bit better of that change of it here. So the domain here has now become the range of the inverse. And we can see that the range here has now become the domain of the inverse. So they basically flip-flop, which is kind of cool to see, okay? So there it is in a little bit better of a format. Now, again, I really strongly encourage you, if you're not familiar with the domains and ranges, use that graphing calculator, but only graph one function. So you'll notice I start with the original function, and that is the only one I actually graphed here. And that's just to have a better idea. If you have too many things in the graphing calculator at one time, it might be confusing. Also, this one, if you were to graph it, it does look a little confusing there, because the sense of what it has is the graphing calculator is not going to account for the fact that this was like a unique domain. So in our sense here, so if I were to put this in the graphing calculator, this is why I don't want you to look at the inverse and determine its domain and range, because this looks like it has a domain of all real numbers, which is totally not the case. And that's because the original did not have a domain and range of all real numbers. So therefore, the other graph is not as either. Okay, but again, it's not as obvious until you start looking at the functions itself there. Okay, so let's look at one more thing, and that's going to be basically, how are these inverse functions, why are they so, helpful? So let's do it in kind of more of a word problem style. So a business property is purchased with a promise to pay off a $60,000 loan plus the $16,500 in interest on the loan. Now they're going to be making 60 payments of $1,275. Now the amount of the money remaining will be paid on the loan plus the interest given by the function. So kind of just to point out where certain things are coming from. So if this is how much the loan is for plus the interest, that means I need to pay back a total of $76,500. Okay. And then since I'm paying that amount back, if I subtract out the payment times X being the number of monthly payments, I can now have a function that basically says how much my loan is. How much is it as I'm paying it off? So how much money is remaining on the loan? Now, to find the inverse, we can basically take that function and kind of work our way backwards with it by doing what we were doing earlier. Now, this is a beautiful linear graph, so linear graphs are one-to-one. Okay, so there's only one that's not one-to-one, and that is the horizontal line itself. So we're going to basically switch that f of x out for a y. Then we're going to switch x and y places, and then we're going to solve for that beautiful new y there. Now, in solving for that new y, we got f inverse, again, that last replacement there, and I ended up with 76,500 minus x all over 1,275. Now, what that does is basically remind yourself x is the number of payments that have been made. So if I were asking you to use the inverse to determine how many monthly payments remain, if there's 35,700 remaining to be paid on the loan, this right here is how much basically is left on the loan. Again, the original function, this was the remaining balance on the loan. This was how many payments were made. So now when I take my inverse there, I can basically use that inverse function of that 76,500 minus x, the number of payments, divided by 1,275. But because x now is the new x, remind yourself, it's literally the x that we originally had was the number of payments, but the output of the original one was the y value. This is kind of that new value, what the y value used to be. So this is how much is remaining on the loan, and this will tell me how many payments I need to make. So if I plug in 35,700, I'm going to get that there's 32 payments that need to be made left on the amount. Okay. And this is where, why is this super helpful? Well, think about it. If you go to, say, Zillow or even realtor.com and you're looking at purchasing a house, you can kind of play with those calculators a little bit, and they will say like, okay, I have a house that is, say, 150,000. If I put this much money down, this is what my monthly payment's going to be. Well, You can also still do that in reverse. So instead of me figuring out, I have this much money to, this is how much the house is, this is how much I want to put down, this is what my monthly payment is going to be. Well, I'm going to probably want to say, well, this is what I can afford. So this is what monthly payment I can afford. I can put in a calculator going the opposite direction and say, I can only afford maybe say $300 or $400 a month. How much would that be in a house for a loan? And then add in whatever your down payment is. And that's basically the price of the house you're going to get. We'll look at this a little bit more later as we start looking into calculating payments and things like that. But that's kind of where that kind of comes in. And this is where those inverse functions really do help us undo something that we've already done, but it might be easier and more mentally understanding ability to use an inverse function versus an actual function itself.